Why is F1
All right. Linear polynomial approximations.
Everyone.
Last. So, Taylor polynomials are created to help us approximate other functions. So the reason we do this is because polynomials are generally much easier to work with, such as taking derivatives or integration. Now, Maclaurin polynomial is just a specific type of polynomial. We'll talk more about that in a moment. But if you hear a Maclaurin polynomial, you will say this is just a very specific Taylor polynomial. Okay. Now, to start, we are going to choose an x value to center our polynomial approximation. We'll call this x equals c. So we'll put, say, some point on my graph as c. Say this right here is c. Right. Our approximation will have the same y value as the original function at c. So we want to write that f of c, which is our function, is going to be the same as our polynomial approximation of c. So we're going to use p as our polynomial approximation. Right. Now we're going to expand the approximation around x equals c. Another way of saying this is the functions are centered at x equals c. So we can do this a couple ways. One, if we draw a tangent line, right? Not a great approximation. Okay, it's a really good approximation at c, okay, or relatively close to c, but not a great approximation. We have used tangent line approximations before, and we talked about whether it's an overestimate or underestimate, right? But we are going to, what are we approximating? The function itself.
What's the rate of change?
We're just going to actually create an approximate function.
So don't we have the function?
Yeah.
Yeah.
Yeah, we're going to create a polynomial function, and it's not going to be a polynomial function.
So we have the graph.
So we have the graph. Again, we may even have a function, okay? But we are going to create a polynomial function, and the reason we're doing that, like I said before, is it is sometimes easier to take derivative integration of a polynomial function than it is the function given. So if we have a function that's not simple enough to take the derivative integral of it, we can create a polynomial function instead. Now, a tangent function is a linear function. We could create, a quadratic function. So one, we could have a tangent. We've done tangent approximations before. All right. Two, we could have a quadratic approximation. And that's probably good around here. Okay. All right. But that would stop relatively quickly on the other side. Okay. Just to let you know, and just to kind of warn you about this, though, is if you see this in different textbooks, some textbooks use A. So they kind of go back and forth. Some use C, some use A. So if you ever see it, it's the same concept. And we're just using C for center. Okay. Now, we are going to do an example of this with our first function here. A function we are given as f of x is equal to dx. So, right, and we're going to center c at 0. Now, the nice thing is to know, what is f of 0? Is 1. So we need p of 0 to be 1. Right? We want to do graphs that have similar shape at the point X and C. They have the same slope. Now, if they have the same slope, what should that lead you to? How do we find slope? There it is. That means f prime of C should equal p prime of C. Okay? To ensure now we really have the same value at 0. This should ensure the same slope. Right? Now, this is going to be a very, very simple linear approximation here. So far, what we have is that e of x minus f of c is equal to f prime of c times x minus c. What is this? What does it look like? Oh, point slope form. Well, we have y minus y1 equals slope of x minus x1. Oh, now we're going to solve e of x. Which just means what? Get rid of x, right? So p of x is equal to, I'm just going to add f of c over f of c plus f prime of c times x minus c. Now, what do we know what c is? In this case, we know c is what? So p of x is equal to f of 0, f prime of 0, times x minus 0. Simplifying this, remember that f of x is equal to e to the x. What is that prime of x? Yes, e dx, which means f of 0 is equal to f prime of 0, which is 1. This gives me e dx is equal to 1 plus 1 times x, or x plus 1. F of 0 is equal to f prime of 0, because they're both the same value. It's f of x and f prime of x, they both e dx. So f of 0 would equal f prime of 0, which is 1. That's only for this specific incident, because f of x is e of x. It's not true for every single time. In this case, f of 0 would be f prime of 0. Right? This is what's called a first order approximation. It works for a small interval around the point of center. Basically, what did we just find? Yeah, you have a table line. Just a different way of doing it. So, if we want f of c to equal p of c, f prime of c equal f prime of c, double prime c equal f, p double prime c, for example, f of 0 will equal p of 0, f prime of 0 equals p prime of 0, p double prime of 0. We do what's called a second order approximation. Yes.
So is x just one approximation of what the graph?
Yes, it's an approximation of the graph.
Oh.
Now that's a first order approximation. We can go further and create a quadratic. Because again, we're creating a polynomial. Technically, a linear function is a polynomial. It's just a first degree polynomial. Okay, we can go second degree, but what do we need for a second degree polynomial? We need the second degree. We want a third, we need the third degree. We just need to keep going. Okay. Now, there's more to this, but not really much more than that. Okay. So, just to show you, I will tell you what the second order approximation is, and then I'll tell you how to get to it. Okay? So our second order approximation, we would have our first order. We'd include the first order, which would be 1 plus x plus 1/2 x squared.
You really want to have those.
That's what we'll show you in the next page.
Oh, you did the middle time, you did the for extension and all this.
Please,
Oh, it's about 100.
the second order approximation of the graph. That we used to.
Yes, that is the second order. So if I created a quadratic function, I'm just curious. Let's go to my graph here and for this. We have second e to the x. And then we have 1 plus x, right? And we'll have this 1 plus x plus 0.5 x squared. Let's see what we're looking at. So the red is my median. My blue is my linear function, tangent. The green is the quadratic. So it is, again, it's getting to be a better approximation. Okay, now the really good way, 0. Okay, we can kind of see that green is the green line, my quadratic is even better, closer at 1 even, okay, than my original function, my linear function. All right, so let's go to the next page. I'll show you where we're getting our information from. So this function, e to the x, happens to have the pattern for my quadratic, or my polynomial approximation, 1 plus x plus 1/2 x squared plus 1/3 factorial x cubed plus all the way down to 1/n factorial x to the n. Now, technically, every single one of these has factorial. You could write this as p to the n of x is equal to 1 over 0 factorial times 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus, I guess you can write x as 0 if you really wanted to make that even more efficient. Okay. What is 0 factorial, by the way? It's 1. Does anybody know why 0 factorial is 1?
There's only one way.
One was already.
What does factorial mean? What do we use factorial for?
It's multiplied by. And you people
That's what it does. What does it mean? What do we use factorials for? It's finding number of choices. Factorial is about finding number of choices. Now, if you have no choice, still one choice. And if you have one choice, you have what? No choice. So 1 factorial and 0 factorial are the same. Isn't that funny? But yeah, 0 factorial is 1, 1 factorial is 1 because they're both the same thing. Yeah. So, and that's why instead of writing 2 factorial, what's 2 times 1? 2. So that's why you don't see the 2 factorial there. But everything else does have a factorial. Okay. Now, we are going to eventually learn that you're just going to have to memorize this one. Okay, there's 4 Taylor polynomial functions you will need to memorize. Our Taylor, polynomial approximations you have to memorize. That is the approximation for e to the x, sine x, cosine x, and 1 over 1 plus x. Okay, they all have very simple patterns to remember. Okay, and you will need to know them. They're not that bad. It really isn't. And I know it's me saying that. But again, I just refreshed this all last week. Okay, well, you better make sure you read it. Make sure I knew what I'm doing. Okay?
So does this mean that?
So yeah, this right here, this approximation is our Taylor approximation for EDX. Okay? We're going to go on further. We're having a few more days of this. We have race and interval convergence, and then finding Taylor McLaurin series. We'll come back to this as well. All this is going to be with these numbers. All McLaurin series. Now, yeah. So, in Taylor polynomial, if x is the principal function, then the approximation f centered about x equals c can be modeled by this right here. Now, we used f of c. Okay, in this case, f of c was just 1. Okay, in our previous one. Here, we don't know what our function is. So, but this is the formula for any basic function. Okay, which is f of c over. Again, you can write 0 factorial if you want, or you can just put f of c. Okay, plus f prime of c times x minus c over 1 factorial. Again, you can just put 1 if you want. Plus f double prime of c times x minus c squared over 2 factorials plus f triple prime of c times x minus c cubed over 3 factorial. Did we see a pattern? Okay, so what is my nth term going to be? F to the nth prime, okay, of c times x minus c to the n over n factorial. Okay, so now we look to Maclaurin polynomial, okay, and that it is a Taylor polynomial. The specific thing about a Maclaurin polynomial is that c is 0. Okay. So how would that create a different function? Well, if c is 0, do we need the minus c's? No, so it's still going to be, well, it's an f of 0. Okay. And again, you don't have to put over 0 factorial because we know that's just plus f prime of 0 times x plus f double prime of 0 times x squared over 2 plus f triple prime of 0 times x cubed over 3 factorial plus f to the n of 0 x to the n over 1 factorial.
Why did you only have the factorial on 3?
Because 2 times 1 is 2.
Why can you do it on the first one?
Just to show you that you can write them, you just don't have to. So like, what is 0 factorial? What? Do you need to write dividing by 1? No. 1 factor is also 1. You don't need to write dividing by 1. So that's why these first two don't have any fractions, because they're just dividing by 1. So you don't need them. And 2 factorial is just 2, so you don't have to write the factorial. Basically, I did it so you guys expressions. All right. So attach conclusion part on you. All right. Yeah.
So with these approximations, we don't actually like go to that.
No.
So do you just
We go to a certain point, and you'll see what the question is going to ask. Yeah. So yeah.
is this related to the error thing we did yesterday, or is that
That's a whole separate. Those are alternating series. Now we will have error dealing with Taylor approximations tomorrow. Lagrange error bounds. That's pronounced Lagrange. Yeah. Yeah, I understand. The first time I saw this, I was, what in the world? I still think this is easier to do than what the first half, because there's not a billion different ways to do one. Okay, we have to figure out which one's the best way to do it. No, this is just do it this one way. You just have to know the complex method that it requires. So find the third degree Maclaurin polynomial for this. Now, again, third degree means we're going to where n is what? 3. We're going to 3. So we'll have 0, 1, 2, and 3. So now it is Maclaurin, which means we're going to be using this up here. That is that P3 of x. That 3 is just telling me we're doing the third degree. Right? Is equal to f of 0 plus f prime of 0 plus f double prime of 0, okay, over 2 times x squared plus f triple prime of 0 over 3 factorial times x cubed. Now, we need to find f of x. What is f of x in this case?
E
to 2x. And what is f prime of x?
to
2x. 2e to 2x. F double prime of x? 4e to 2x. And f triple prime of x? a to 2x. Why do we need that? F of 0 is 1. F prime of 0 is 2. F double prime of 0 is 4. F triple prime of 0 is 8. So we just plug in our values. And this is the nice thing about Maclaurin polynomials. We don't have to FOIL anything or raise anything to a power. I would say if you're doing a tailored polynomial, it would be beneficial to know Pascal's triangle. Okay.
What is that?
I'll wear my Christmas tree shirt tomorrow. I have a Pascal triangle Christmas tree shirt. Of course I do. Pascal's triangle are a way of multiplying a polynomial, a binomial to a power, to any power. It gives you the coefficients. Okay. So that's how you know that if you square a binomial, it's the coefficient of the first term is 1, the coefficient of the second term is 2, and the coefficient of the last term is also 1. That's why you square the two terms and then multiply them together and double it. The reason why you double it is because the coefficient of the middle term is 2. If you cube a polynomial, is the first term cubed times 1, the first term squared times the second term times 3, because the coefficient is 3. First term times the second term squared times 3, and then the last term cubed. If you know Pascal's triangle. It's again, do you have to know it? No, it just would make things faster. Anyway, yes.
So for like the full normally right now, when you set how many zero times x?
Right. Let's see x in there. Let's see here. P3 of x. Let's plug in our values. So f of 0 is 1. F prime of 0 is 2. F double prime is 4 over 2. X squared. And then 8 over, what's 3 times 2? 6. X cubed. And you can simplify this to be 1 plus 2x plus 2x squared plus 4/3 x cubed. There it is. This right here is generally an FRQ. Okay, this right here, you don't have to reduce that for your FRQ. Okay, if you have this, you don't have to really simplify it. Just once you get to that. You can't.
So the very the final.
You need x there because c is 0, not x.
But x
For it's centered around c. It's not always. X equals c is the center of it. That's where we get the f prime of c, this double prime of c, right there. But x in a function, we still have the x here, here, and here, all the time. Because we need those x's to make a polynomial.
Oh, it's the tailored polynomial. It is x equals c.
Yeah.
And this is the Maclaurin.
Where c is 0. Now it says evaluate f of 2 and then p of 2. So what we're going to do is we're going to show the difference between the true value. Okay, so what is f of 2, 0.2, it's e to the 0.2. And then if we have this, okay,
E 0.4? It's 0.2.
oh yeah, times 2, right? Because I read the actual function, we got 2 times 0.2. And then we have our function, which is 1 plus 2 times 0.2 plus 2 times 0.2 squared plus 4/3 times 0.2 cubed. Right? So if you plug this in, you would get that this degree 1.4918. And this is 1.4906 repeating. So only to the third degree, only to the third term, we're only off by like a thousandths of a decimal point. So it's again, a really good approximation. We're only going 3. We could go 4 or 5 pretty easily. It's okay. And get even better approximation. So now we have this one.
This is equal to 1. And yeah. Makes sense that.
Find the fourth degree Taylor polynomial for ln of x centered at x equals 1. So here C is 1. So this is a Taylor, not a Maclaurin, because for Maclaurin, this would be x equals 0. So that means to just write this out, p to the fourth term is going to be what? F prime of c, in this case is 1. No, f plus f prime of 1 times x minus 1 plus f prime, double prime of 1 over 2 times x minus 1 squared plus f triple prime of 1 over 6, because you already know 3 factorial is 6, times x minus 1 cubed plus f to the 4th. Now, if you go up to 4, you just put 4. You can put 4 dash if you want, but it gets real messy. Anything after 3 is just a number, 4, 5, 6. So we have a 1. Now, 4 factorial is basically 4 times 6. You just keep multiplying by the next number. 4 times x minus 1 to the 4th. Now, you are not going to have to actually multiply it. Okay? If I was real mean and they wanted a true polynomial, then yeah, you would have to multiply, raise that squared to the cube to the 4th. Okay? But we're not going to do that. Okay, you can leave that as it is, x minus 1 squared, x minus 1 cubed, x minus 1. Okay. Now, we're doing the same thing we did before. We need to find f of 1, f of x, which you know will be natural log of x. Right? What's f prime of x? X, f double prime of x, negative 1 over x squared, f triple prime of x, not 1 this time, 2 over x cubed, and then to the 4th, like sort of 0. Yeah, multiply by 6 and negative 6 over x together. So it's going to alternate. Okay, this is going to alternate. So we need f of 1. What is the natural log of 1? 0. F prime of 1, what's 1 over 1? 1. F double prime of 1, negative 1 over 1 squared, negative 1. F triple prime of 1 gives me 2 over 1. And then f to the 4th, and then 4 to 1 is negative 6. So, plug all that in. Get 4 of x. F of 1 is 0. 1 times x minus 1. Negative 1 over 2 times x minus 1 squared. So again, I'll simplify all the negatives. We'll simplify this in a second. I'm just plugging back in. Nice. Hey, you taking a test? Yes. Okay. Let me do this. Wait a minute. Alright. So we had the prime triple prime, which is 2 over 6 times x minus 1 cubed, and then lastly negative 6 over 24, which is x minus 1 to the 4th. Now this actually gets a little interesting the way this works. We're going to give me again, not just gone. I have 1 times x minus 1. Again, I don't have to write the 1 there. You can leave it as just an x minus 1. Right? Plus, well, not plus, minus, right? Minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed minus 1/4 x minus 1 to the 4th. Yeah. 1/2, 1/3, 1/4. So it's an alternating function with 1 over n times x minus 1 to the n. That's what that Taylor polynomial would be.
So this is all we need. This is all we need.
That's all you need. Now it says evaluate. So what is f of 1.1? If we do the natural log of 1.1, you get 0.09531011798. I think you have to go that far, but you go. And then p to the fourth of 1.1, you plug that in, you'll get 0.0953083 repeating. So we get all the way down to what, the 100,000th place? Again, are we far away from the center?
No.
No, we're not far away. So we should have a really good approximation close to the center. Okay. Well, so coefficient of the nth degree term in the Taylor polynomial, the function set of x to c. We've already been kind of writing this. Okay. Remember that the nth term of a Taylor polynomial is f to the n over c times x minus c to the n over n factorial. Basically, just bring that out. What do you get? This is your coefficient. Right? So if you're asked for a very specific term, you don't have to do all the work that we just did. Just find the coefficient and multiply it by x minus c to the n power.
So all you have to do is that.
If it asks for the coefficient, like number 3. So let f be the function of the third, with the third derivative form. That's fun, they give us the third derivative form. Okay, which is nice because what do we have to do if we want the coefficient for the fourth term? Yeah, 2 over root. What's the coefficient of x minus 2 to the 4th in the 4th degree Taylor polynomial graph if x about x plus 2? So that means we need, well, we know f of 4 to the x. So what's my derivative of my next term? So take the derivative, what we get, bring down to 3/2, right? So 3/2 times 8x plus 2 times 8, which is going to give you up to the 1/2 power, which is going to give you 12 times square root of 8x plus 2. No. What do I have to do to find the coefficient? Go to the center. What's the center? 2. So 3 over 2, well, that would be 12 times the square root of 8 times 2 plus 2. We need 12 square root of 60 plus 2, 18. So what's the square root of 18 as a radical?
3
Root 2. So 12 times 3 root 2 is 36 root 2. Now, that is my f of n. See, that's my numerator. Numerator. What's my denominator?
4
4 factorial 24 is my denominator. 36 root 2 over 24, and both 36 and 24 are divided by 12. Here are 2 root 2. That is your coefficient. All right. You have your homework. I'll post the answer to you.
Yes, sir.
Oh, you can hand me the paper.
Can we get it back before the test?
Yeah, let me make sure I give you guys all your work backs.